Welcome to the fourth session of the training Thorium Molten Salt Reactor Technology with Professor Kun Chen. Yeah, introduction to Thorium Molten Salt Reactor Technology and safety design. Okay, so Kun, without further ado, I would like to give the floor to you, please.
Thank you very much, Bob. Let me start with sharing my screen. Put it into presenting mode and just get out the pointer. Okay. Can you guys see my screen?
Yes.
Okay, wonderful. Welcome everybody to our weekly workshop on introduction of ThorCon molten salt reactor technology and safety. So today we're having the week 4. We just had a 3 very successful workshop in the past weeks. Last week we had Lars and Manu give the introduction on the neutronics and the thermohydraulics. Today we're going to talk about the operation of the power plant and the balance of the power plant. We think the operation section is very important because this is where the power plant and the core spend most of its time during its lifetime, because normal operation is what you do every day, and accidents are very rare, even though they're important, but they're very rare. And also every accident, every anticipated operational occurrence arise from normal operation. So it's very important for us to understand how we're going to operate this power plant and how the components and system behave during the normal operation. So in the next 2 weeks, we're going to go into the details of each individual systems. In this week 6, we're going to talk about the DBAs, safety analysis, which will be based on the normal operation. And Bob and I just talked before we started. We may have a week 7 session to answer the questions that everyone had. Okay, so today we're going to talk about the operation and BOP. We have 3 main topics for today's workshop. How do we operate the reactor, and especially how do we do the load following, because this is a very interesting topic, and ThorCon 500 definitely has the capability of load following. We want to do a quick review on how that would work. So what load following means, the power of the power output of the power plant can be adjusted to suit the demand of the utilities. So, and the last, we're going to talk about the balance of the plant, the BOP. So those are the large part of the power plants. They're not safety related, but they're very important for a operation of the power plant. Let's go to the next slide. So we start with normal operation, but let's visit the definition of the normal operation. See how the slides go. Just give me a second. The slide is. Oh, okay. So each country has their own definition of the plant states, but now here we're using the IEA's definition. As you can see on the screen, IEA defines 2 basic categories: operational states and accident conditions. So within operational states, there's normal operation, there's anticipated operational occurrences. So what the difference is, the anticipated operational occurrences has a limit on the frequency of its occurrence, which should be larger than 10 to minus 2. So, and then in accident conditions, we have DBAs, and then we have a design extension conditions. Today, we're going to focus solely on normal operation, which is to the left. And we're going to touch base a little bit about AOOs. And we're not going to talk about the DBAs and DECs in this presentation. We're going to talk about those in the future sessions. Okay. Yeah. Okay. Before we go into the details, I'd like to spend a few minutes on the terminologies we're using for ThorCon. So we're using a slightly different terminologies compared to the traditional nuclear power plant because our design is different and we're using a modular design. So in our design, we call the reactor core to be pot, which is really a pot shape container. And the can, which is really equivalent to the reactor in the traditional nuclear power plant. And what the traditional MPP does not have is the power module because we're having a ThorCon 500 is modular design. So we have the concept of power module, which we call PMOD, which is 1 unit of reactors and supporting equipment. And then we have fission island, which is equivalent to the reactor building in the traditional power plant. What the traditional power plant does not have is a fuel drain tank, which is a unique feature with ThorCon 500. And this fuel drain tank, it can hold the fuel, maintain subcriticality by geometry, and cool the fuel passively and contains the fuel. We're going to see a lot of this during our normal operation. And then we have freeze valve. So the freeze valve is basically, it cools the salt to solid in a section of the pipe to stop the flow. And of course, we're able to freeze it. We're also able to melt it. And that freeze valve work with the fuel drain tank is the basic safety systems for ThorCon 500. And then we have a red tank, which you will see in the next few slides. It's really a steel tank with lead layers and filled with borate water. By the description, you can guess that the red tank serves as a shielding system, and also it's part of the containment boundary. And then we have a 3 definition of fuel salt. Fuel salt is our fuel. We call it fresh when it's unirradiated with very low radioactivity. So it's basically uranium or thorium, which hasn't take any chain reactions. So it's fresh fuel. But we do have another concept called non-fresh fuel salt, because the fuel salt has a lifetime of 8 years, but the reactor itself only has a lifetime of 4 years. So that means the fuel salt will be used in 1 can, then be transferred to another can for a reuse. Because we're reusing the fuel salt, so we have a definition called non-fresh fuel salt, which means the fuel salt has been used in 1 can, but still can be used in another can. And then we have used fuel salt. That means the fuel salt has been used in both cans, it reaches 8 years lifetime. It has to be unloaded from the core, so we call it used fuel salt. We're not calling it spent fuel. We call it used fuel instead of spent fuel, because we think for the used fuel, there's a valuable material that can be used in the future. So it's not spent, it's not a waste, it's actually a valuable asset. So those are the some of the definitions we have, and hopefully this will help you to understand the following several slides. Okay, let me get to the next one. Okay, so let's review the fishing island a little bit. As I said, the fishing island is equivalent to the reactor building of the traditional power plant. This is a cutaway view of the fishing island. As you can see, each fishing island has two power modules, one on the left, one on the right. For each module, there's two cans, and at any time, one can is in power operation, and the other can is cooling down. The pot, the core, is of course within the can, which you cannot see from this picture, but you will be able to see it in the next picture. So within each power module, you have not only two cans, but also have a secondary loop. So two cans share one secondary coolant loop. But remember, at any time, there's only one can in power operation. That means the secondary loop only circulates to one of the can. And the other can is actually in cooling down mode. So there's no circulation to this side. So after the secondary coolant salt loop, we have this tertiary salt loop, or sometimes we call it solar salt loop, because the salt is also used in concentrated solar power. So this is the solar salt or tertiary salt loop. And then we have a steam generator, which generates steam and feed the steam to the turbo generators in the rest of the power plant. And one important feature I want to point out is, first of all, there's a fuel shipping cask vault here. So whenever we transport fresh fuel, we drop the fuel shipping cask into this vault. And on top of that, as you can see, this is the what we call rat tank. It serves as a shielding, and also it's part of the containment boundary. And on top of the rat tank, you can see the floor here that people can walk on the floor during the power operation. Because of the thick shielding, you can walk freely when the can is running. And of course, on top, you can see the hatches. So in order to get access to the can and fuel shipping cask, you have to open the hatches, which we'll go through that in the next several slides. Okay, so let's take a closer look into the can. Now, this part is the can, and then under the can, it's a fuel salt drink tank. And outside of the can is the cold wall. So the cold wall basically cools the can and fuel salt drink tank passively through natural circulation of water. And here's the pot, which is the core. As you can see, why it's called pot, because it looks like a pot. So the fuel salt circulated within the can. And there's several things I want to point out is that, first of all, there's a fuel makeup tank here, which is important, this tank, because we're going to add makeup fuel salt into the system during operation. So we'll talk about that. And then there's a thorium tank. So we're adding thorium into the primary loop. Basically, we're adding into the pot. So those two cans serve the purpose to adjust the amount of fissile material in the pot, therefore adjusting the reactivity of the system. It is a very important feature because we're not using control rods to adjust, to do the small adjustment of the reactivity. We're using adding and removing sort, which is very convenient for us. The other thing I want to point out is, as you can see, this outlet temperature and inlet temperature, which we call typical temperature. Why are we saying that? Because this is a load following system. So this temperature shown here is the operating temperature at 100% operating power. When you reduce operating power to follow the demand, this temperature will change, which we will see in the future slides. The last thing is you see there's two valves here. This is the secondary salt loop. So because we're replacing the cans every 4 years, so whenever we have to replace it, we have to cut the connection here. So this valve will stay with the can to isolate the can from the environment. So every time we disconnect it, we will have to shut off the valve. And when we connect it, we will have to open these two valves to let the secondary coolant loop circulate. Okay, hopefully this gives you a general idea of the system. So let's go to the normal operation. Okay, so ThorCon 500 is a modular design. That means at any given time, the cans or the reactors in the power plants may be in different operating mode. For example, one can be in power operation, the other can be in cooling down state, and the third one might just be replaced. So it makes sense to define the can mode rather than the plant mode, because each plant usually have 4 cans at the same time. So following this slide, every time we talk about the mode, operating mode, we're talking about the operating mode of the can. Okay, so the diagram on the right shows all the operating modes for the cans. So it starts with mode 1 all the way to mode 14. So they're not the same. They're not describing one scenario. Actually, they're describing several scenarios. So, for example, if we have a new can coming to the power plant and it's going to use the fresh fuel salt, it will go through a mode 1 all the way to 7, 8, 9, 10, and 11. So this will be the pathway. However, if we have a new can, but we're using non-fresh fuel salt, which means the fuel salt has been used in the other can, in that case, we will start with mode 13 to 14 and go back to 3, then all the way to 11. And then we have an island mode, which means when you go from the startup to the power operation, now all of the sudden you don't need the power. So then you go into the hot standby mode, which is 7, which allows you to stay there for a very long time. And whenever you have a new demand of electricity, you can immediately go back to ramp up the power. So you can see the circle here, which allows you to go to standby and back to power operation. And there's other 2 scenarios. One is restart from shutdown. So if you shut the can down to mode 8, you can restart it fairly easily back to 3. And you can even restart the can after you drain the fuel salt. So once you drain the fuel salt, you have to go through a transition mode, then you go back to mode 3. So this basically describes the typical normal operation of the can. So we can go to each mode one by one to give you some idea of how each mode would work. So let me go to next step. Okay, so how do we start? So the power plant itself will be manufactured in the shipyard and will be towed to the operating site and then set on the site. And then we'll have a can ship, which you can see in the middle. The can ship will transport the cans, and also it will transport the fuel. So this small hole here, it shows the position to hold the fuel shipping cask. So as you can see, you have to load the can from the ship into the power plant, and then you have to lift the fuel shipping cask out of the can ship and to the power plant. Now here we're showing two ThorCon 500, but our first demonstration power plant will only have one. Okay, so let's say we're ready. So how do we start the power plant? So we enter the mode 1, which we call the cold pre-startup. So what we do there, now here I only list the major steps. There's more steps here. We do have a document that describes the detailed operation, but here I'm only listing the most important ones here. So first of all, we have to remove the hatches, which you can see on the screen. It basically covers everything, so we have to remove that. And then you have to remove the rat tank. So this is a rat tank, and you have to expose the can silo so you can load the can. Now there's a ring on the main deck of the power plant that allows you to remove those hatches and the rat tank. So I can go back to the previous slide. You can see the ring here. It can remove hatches. It can load and unload cans. Okay. And then once you expose the can silo, you can install the new can. And of course, you need to connect all the pipes and cables. It's very important is 2 secondary loop lines, as I pointed out in the previous slide, which you can see here. Those are the 2 secondary loop lines. So I'm mentioning them because they're big pipe with a half meter in diameter, and other pipings are much smaller. The cables are much smaller. And then you have to install the fuel shipping cask into here, because you need both cans and fuel, right? So, and then after you've done that, you reinstall the rat tank, you reinstall the hatches, and then we purge and fill the system with helium to remove oxygen and water. Okay, so we call it a cold pre-startup because in this mode, we're not heating up the system. Almost all the operation is happening at room temperature. Okay, so once we've done this, of course, we have to do a lot of testing and checks, make sure that everything is okay. Once we make sure everything's okay at the room temperature, we can start to heat up the system. So then we're entering mode 2, which we call hot pre-startup. So in this mode, we heat up all loops and salt tanks to the temperature above the liquidus temperature of the salt. So make sure the salt is melted. And then at that temperature, we have to perform the leak rate test, make sure the containment boundary is functioning. And then we flush the loops with molten flash salt to remove oxide. So we're not filling the fuel salt or coolant salt directly. We fill the flash salt first. This step is to remove oxides that may exist on the inner surface of the piping of the vessel. So once we flush the sort, we're gonna close the freeze valves. So how do we do that? So the freeze valve has a band that when you flush the system, there will be some residue sort left in the freeze valve. Then you can freeze those sort to be solid, and then you can stop the flow. So the freeze valve will be formed in this phase, in this mode, sorry. And then we insert shutdown rods. Okay, so once we insert shutdown rods, we will be safe to it will be safe to transfer the fuel sort into the can. And of course, we have to verify the volume because it's not only important safety, but it's also important for safeguards. We want to make sure that we know where the nuclear fuel is. And after that, we're going to close the containment system boundaries. Remember, we have 3 containment systems, so all will be closed. And then we remove the fuel shipping cask from a system. So at the end of mode 2, the system is ready for startup. Then we can enter the mode 3 startup. So in this mode, first of all, we start the off-gas system. It's not clearly shown on this picture, but you can see this off-gas recuperators, which the off-gas goes out from the pump header tank to this recuperators, and it circulates in the off-gas system. It has to be started first. The off-gas is mainly helium. There's once in power operation, there will be xenon, krypton, and other gaseous fission products. And then we start the primary loop pump. So we always keep the primary loop pump in a constant speed. So that simplifies the operation. So we start that. And after we start that, we reach the shutdown rods. So we basically withdraw the shutdown rods from the pot. Now we're able to do that because when we fill the fuel sort, it doesn't have any excessive reactivities. So even if we raise it, it won't reach criticality by itself. So how do we achieve criticality? We do that by adding makeup fuel sort from the makeup fuel tank, which is here. So we'll keep adding additional fuel sort into the system until it reaches criticality. Now there's a limit for adding additional fuel. We're limited to 0.2 ppm per second or less. And so slowly, the system will approaching criticality, and eventually it will reach criticality. The whole process will likely to take 4 hours. We have a monitoring system. If anything goes wrong, the shutdown rod will drop into the pot and will stop the chain reaction. So once we reach criticality, we'll keep ramping up power to less than 10% of the full power. So how do we do that? We do that by increasing secondary pump and tertiary pump speed and adjusting bypasses, which we'll talk about that in the next several slides. Okay, so by the end of a startup mode, we're in a low power operating mode, which is less than 10%. And then we can go to the next mode. So mode 4 is really relatively simpler. It increased power from under 10 to 40, and then we can reach power operation mode. And in this mode, we're doing load following. That means the power output can vary from 40 to 100. And then if we want to reduce the power, we have to go to another transition mode, which is mode 6. It decreases power from 40 to 10. So I will have several slides to explain how do we increase and decrease power. But let's finish this mode first. Okay, so mode 7 is what we call hot standby. So in this mode, it's actually directly from mode 6. Remember, in mode 6, we decrease power from 40% to under 10, but now we're keeping this power under 10%, but sufficient for the operation of the plant itself. So that means the power plant only generates enough power for itself. It doesn't output the power to the power grid. So no power to the grid. And what if we have excessive power for any reason? Then we would dump those excessive power, meaning steam, to the condenser. And we call this island mode, because thinking about this, it doesn't need any connections to the outside world. It will be self-sufficient, and it can keep in this mode for a very long time. So why we need this mode? Because sometimes we will lose the grid for whatever reason. Could be weather conditions, could be the grid does not need any power. So whatever happens, we will enter this hot standby mode. And the benefit of entering this mode is we can ramp up power immediately when the grid is restored. So in this mode, if there's a need for power, we can ramp up it immediately. So this is mode 7 called hot standby. But what if we don't want to run the power plant? If we want to shut it down, then we enter mode 8, which is hot shutdown mode. So in this mode, we first insert shutdown rods, which will stop the chain reaction. And then we decrease the pump speed to maintain temperature, because there's still residual power, decay power, and other source of power. So we have to still run the pump to remove the heat. And the decay power will be enough in the first several hours for the operation. But after that, the decay power will be very low, and it won't generate enough power and steam to power the plant itself. In that case, we have to take power from the outside world. If it's not available, then we have to use the diesel power for a long time operation in this mode. So as you can see, the hot shutdown, even though it's shut down, it's not intended to be, the plant is not intended to be in this mode for a very long time. And of course, the reactor can restart from the hot shutdown. It could just restore the shutdown rods and doing some adjustment on the fuel volume. Then it will go back to the restart mode. So what if we want to shut the back down for a long time? If you want to do that, we need to enter the cold shutdown mode. So first of all, we have to clarify that even though we call it cold shutdown, it's not really cold. Okay, at least it's not started with a cold temperature. So the first step is to stop the pumps, and then we stop the off gas system, And then the important step is to open the freeze valve. So which is here, as you can see the freeze valve. And then next we drain the fuel salt into the fuel drain tank. So the salt will be out of the pot and will go to the fuel drain tank. Okay. So the benefit of doing this is, first of all, the geometry of the fuel drain tank ensure the subcriticality. So even with perturbation, it will remain subcritical. Also, because of the Cold War, the natural circulation of water, this fuel salt will be cooled passively in the fuel salt drain tank. So no worries about the overheating. And then the fuel tank is it's a containment boundary, so it contains the fuel salt. And most importantly, all these functions do not require power. So theoretically, the fuel can stay in this mode for a very long time, even though even to like half a year or a year. So we call it safe shutdown mode. So in this mode, it's doing the control, it's doing the cool, and doing the contain, and for a very long time. So we call it cold shutdown mode. Okay, so what if the fuel salt has reached its lifetime, or the can has reached lifetime? We want to replace it. Then we're going to enter the post-operation cooldown mode, which is mode 10. So what happens in this mode is we transfer the fuel salt to the other can in the same P mod or to use fuel whole tank from the fuel drain tank. So remember, in mode 9, the fuel salt is all in this fuel drain tank in this can. Then in mode 10, we want to drain the fuel salt, or transfer the fuel salt out of the fuel drain tank. We could either transfer it to another can, because there might be a new can come in and the fuel salt can be reused. Or if the fuel salt reaches lifetime, we will drain the fuel salt or transfer the fuel salt from the can to a used fuel whole tank, which is just underneath the secondary coolant pump, which you don't see here, but there's a used fuel whole tank underneath. So in this case, there will be almost no fuel salt in the can. There will still be very small amount left, but the majority of the fuel salt will be in the fuel whole tank. So in this case, we will fill the can with helium and isolate it, and let it stay here to cool it for 4 years. Again, the cooling is passive by the Cold War. So this mode 10 typically takes 4 years for the can to cool down after the fuel is removed. After 4 years, when the radioactivity is relatively lower and the temperature is lower, it's ready to be removed, because every 4 years we have a new can. So this can stay here, operated for 4 years, cooled for 4 years. After 8 years, it'll be removed, a new can will come. So in this mode 11, we disconnect the can, and then we remove the can from the plant. Of course, we have to open all the hatches and red tanks, but I'm not going to go into the detail here. So from mode 1 to mode 11 basically tells you what's going to happen to a can during its lifetime. So now what is mode 12 here? So remember, in the last mode, in this mode, the salt is in the fuel drain tank. But now we're saying, okay, what if we want to reuse the fuel salt in the same can? Can we actually push it back to the pot? Yes, of course we can do that. So now we're entering mode 12, It's transition from cold shutdown to startup. So that tells us how do we push or transfer the fuel from drink tank back to the pot. So first of all, the shutdown rod has been inserted in the previous mode. So in this cold shutdown mode, the shutdown rods are it's already inserted, and then we transfer the fuel from the fuel drink tank to the can by using helium gas to push the sort back to the pot. Now, there's one thing we have to worry about because the thorium fuel, after irradiated, it generates a Pa-233, and it decays to uranium-233. So if you let the fuel salt to stay in the fuel drink tank for a while, it will increase the quantity of uranium-233. So we have to compensate that. Otherwise, we'll have too much fissile material in the system. So we do that by adding thorium salt. So we push it back, and then we add thorium fuel into the pot, which will push some of the fuel salt out of the system. So with the mix of thorium salt, it will reduce the total amount of fissile material. So this mode is important because imagine we have this freeze valve. If for some reason it accidentally opened and drain the fuel salt to the fuel drink tank, which is not a safety concern, but we don't want to throw everything away. We want to reuse the system. Then this mode is very important for us to transfer the fuel salt back to the pot to restart the reactor. So this one is mode 12. And then we have 2 extra modes, which is for the case, for the scenario that you're not using a fresh fuel salt. Say the fuel salt has been used in one can, but then you want to use another can. So these 2 modes prepare the can ready for the non-fresh fuel. So I'm not gonna get into detail here. I know it's a little bit confusing because we have so many modes. So we do have a summary of the modes in this table. I apologize for the small fonts here. But as you can see, we have a total of 14 modes. And this is the number of modes are more than what you usually see in a light water reactor, because first of all, we're a modular design that we have several reactors, several modules going on at the same time. So you will have those modes. And then we're also reuse the fuel salt. So we're not just throw the fuel salt away. When we replace the cans, we reuse the fuel salt. So those modes that from 11 to 14, those basically added for the modular design and fuel salt transfer. And the other 2 modes, 9 and 10 here, are just for replacement of the cans. So the operation is very similar, but we have more modes for replacing the cans or transfer the fuel. And now we have this table that at least summarize all the modes. So I'm not going to go into details, but I will. Once we share the slides, you will see the summary here. So the intention of defining this mode is to make sure that we understand how the power plant operates. So make sure we cover everything. So every normal operation will be covered by these modes. Once we understand that, it gives our initial conditions for the accident analysis. So every accident arises from normal operation. So for each mode, for each operational mode, we will think about what what can happen, what bad things can happen, what PIEs can we have from each of the mode. So then you will have a systematic approach to identify everything. And then you also have the initial conditions for your accident analysis. So one of the major topic for the normal operation is the load following power operation, which is mode 5. So we didn't spend too much time there, but I like to spend time here to explain how we're going to do the load following. So the load following is interesting because in today's electric market, there's all kinds of electricity sources. Some sources can stably operate for days, weeks, and months, like nuclear power. Some sources cannot, like wind power and solar power. They're not always available. So, and also on the demand side, the consumption of the power it's not constant. So the grid has to adjust its power output, and the load following is a way for the power plant to adjust to feed the demand from the consumers. Now, so how do we do it in ThorCon 500? Now, first of all, I want to do a review of the heat flow. Now we have this pot. So we have first loop, which is the fuel salt loop. We have a pump. We call it the primary loop pump. Then we have the secondary loop, again, the salt loop. Then we have the tertiary loop or soda salt loop. It's a third loop, again, it's a salt loop. And the fourth loop is a steam loop. So we have this feed water pumps and everything that circulates steam and water. And there's also bypasses. So from each loop, except for the primary loop, all the secondary loop, tertiary loop, and steam, they have bypasses. So what we can adjust is the pump speed and the bypasses to follow following the load. So exactly how we can do this, let's go to the next one. So the picture on the right, as you can see, there's two cans. Of course, one is in operation and the other one is in cooling down state. So let's say, assume this one is in operation. This is the primary loop here. And then there's a secondary loop, tertiary loop or soda salt loop, and then steam cycle. So how do we follow the load? So first of all, we adjust the feed water and hot well pump speed and bypass flow rate for the steam cycle. But by doing that, we keep the steam temperature near constant. So we're not adjusting temperature. We just adjust the flow rate of the loop, which I have some curves in the next several slides. I can go into detail, but let's go through the whole process first. So we adjust the flow rate of the steam but keep the steam temperature near constant. And to match that, we adjusted the tertiary or soda salt pump speed and bypass. So again, we adjust the flow rate to match the steam cycle. And then we adjust the secondary salt pump speed and bypass flow rate to match the soda salt loop or the tertiary salt loop. And then we keep the fuel salt pump speed constant. So for the primary loop, we don't adjust the flow rate. Instead, we let the fuel cell temperature to change. So the fuel cell temperature will match the need from the secondary loop. And because the fuel cell temperature changes, the fission power will follow because the negative temperature reactivity feedback coefficient. Okay, so let's go to some curves here. So let's start with steam cycle. And as you can see, from power 0 to power 100, which 1 means 100% power. And you can see we maintain the steam temperature almost constant throughout the process, but we're changing the pump speed, which is not shown here, but I will show it later. And then to match that, we have to keep the solar store temperature almost constant with a little bit change. And we also adjust the bypass, but the pump speed will change. Okay, so this is the solar loop temperature. And the next one, this one is a secondary soil temperature. So secondary soil temperature increases following the power, but you can see the temperature difference here remain constant throughout the power change. And that means we have to change the flow rate, right? Because the temperature difference is the same, then you have to change the flow rate to change the power. But going back to the fuel cell temperature, as you can see, at 0 power, there's almost no temperature difference between the hot and cold leg. But when you increase power, remember the fuel cell pump speed is constant, so the flow rate is constant. So the temperature difference will increase, and temperature will change. It's automatically followed. With this temperature change, the reactivity will change, the power will change. Okay. So to make this more clear, I'm showing you the pump speed. So this is the primary loop pump speed. It's always constant throughout the power change. And the secondary pump speed, which we're using a flow rate here. So the secondary loop flow rate and solar loop flow rate are increasingly together. They're overlapped, so you don't see two, but they're two are the same. So when you try to increase power, you increase the flow rate of the secondary loop and the solar sort loop. And then you adjust the bypass. These are the bypass. So by adjusting the pump speed and the bypass, you will achieve the power change. So hopefully, I mean, this is more obvious when we run the simulation. It's not very straightforward from the slides, but hopefully this gives you a general idea how the load following will happen. And the typical power change rate is about 1% of full power per minute. That means if you want to increase power from 40% to 100%, it takes you about an hour. But there's a maximum power change rate, which is 5% per minute. If you do that, it's only takes you one fifth of the time in the typical mode. But usually we want to keep the power change rate as low as possible unless it's necessary. And you can see the fuel cell temperature at the outlet is highest at 100% of power. So we can go back to the previous slides. So that means the fuel temperature, the fuel temperature is highest at the forced power mode. Okay, so hopefully this gives you some idea about the load following. We can get into this in more detail if you have more questions about load following. Okay, so the third part of the presentation is about the balance of a plant, because the steam turbo generators, the switch yards, they're all in this part. And it's very important for power generation. It's not a safety concern, but my thinking is that the power plant is built to generate reliable power, right? It's not only to defend against the accident, but more importantly, it needs to generate reliable power for people. So it's very important for the plant to be powerful, to be efficient, to be economical. So BOP is actually very important in terms of operation. So what are the BOP parts? So from this picture, you can see this is the fission island, which equivalent to the reactor building of a traditional power plant. It contains the can, which is the reactor itself. But after that, this part is all called balance of a plant. It's not radioactive. Mainly, there's several parts, but mainly there's a turbine hull and a GIS hull. And GIS hull stands for gas insulated switchgear. Of course, there are several other parts like the operation house, like buildings, people can live there, can operate the power plants. There's cranes here. There are small structures on top of the main deck, but the majority of the equipment in the BOP stays in either turbine hull or GIS hull. Okay. So, but let's spend a few minutes to get us familiar with some basic shipyard terms. Now, ThorCon is using shipyard terms when describing the power plant. The reason is the power plants will be built in a shipyard, so it's necessary for the shipyard to understand. And so that's why we're using the shipyard terms. And also the layout of ThorCon 500 is quite different or unique compared to the traditional power plant, because in the traditional nuclear power plant, the layout is generally flat. So you have a large area, and then you have buildings, several buildings. You have reactor buildings, you have office buildings, you have pump buildings, you have some storage buildings, workshop buildings, and that spread on the map, right? However, the ThorCon 500 integrate everything into one large building here, and it's more like a ship. There's several floors, so which you don't often see in the traditional power plant. So in order to accurately describe the layout using the shipyard terms will be very helpful. So, but the issue is that people who are working in the nuclear industry are not familiar with the shipyard terms. So it makes sense for us to get some basic understanding on some a very simple shipyard term. So first of all, let's start with the deck and hull here. So in the building, we call it floor, but in the ship, we call it deck. So I think I assume everybody knows that, but we're going to keep using the word deck in our layout. And then we use hull, which basically the ship. So we use that to refer to the building of the plant. Now, a typical traditional LWR plant will have several, more than one buildings, but we only have one hull. So that's a major difference there. Then if we look at the ThorCon 500 as a ship, so at the forward section, we call it bow, and the end, we call it stern. So that's how you call a ship, right? On the left, if you look forward, on the left, it's called port side. On the right, it's called starboard side. And then directions, forward, that's easy to understand, but backward, it's called aft. So this direction is aft. If we say something is aft or looking aft, that means this direction. And then we have inboard, which is easy to understand. Towards the center, it's called inward, and away from the center, it's called outboard. So those are some basic shipyard terms will help us to understand how ThorCon 500 is laid out. Okay, so I'm starting with a very crowded diagram here. And here's a typical steam cycle diagram of ThorCon 500. I don't expect you to see every details here. I'm not going to every details here, but the slides will be shared with you. In this presentation, I'm just gonna focus on some important things here. So as you can see, the steam is generated from a steam generator. It drives the high pressure turbine, and it drives the intermediate pressure turbine, and then to the low pressure turbine. So there's 3 turbines here. And then the steam goes to the condenser, and then it pumped into the low pressure feed water heaters. There's 3 heaters here. And after that, the water will go to the aerator right here to remove the oxygen, carbon dioxide, and other gases. And then it will be pumped by the main feed water pumps into the high pressure feed water heaters. Then we feed back to the steam generator. Okay, so this is the main cycle. And then of course, there's always a bypass and other cycles to improve the efficiency. So 2 features I want to point it out here. One is this called century turbine here. So this turbine, as you can see, generate 15 megawatt electric power. This power can be used to operate the power plant. So during the normal operation, the steam will be coming from the main steam generator. But when you lose the main steam, this century turbine can be powered by an oil boiler in the plant. So it is very important to have this, so that when you lose the fission power, when you lose the grid power, you can keep the power plant in the hot standby mode for a while. The other feature is the bypass here. You can see the steam can bypass all the turbines and go directly to the condenser, and it's cooled by the seawater. So when you have excessive power, let's say you have excessive steam, you can dump it to the condenser. So that's give you the flexibility. So if you don't need the power, you can just dump it into the sea. This setting gives you a net efficiency of powerful cell, which is 46.4%. Of course, it's based on several assumptions. It's based on the temperature of the seawater. It's based on several other assumptions, but you can get the idea of the efficiency of BOP. The 45 or more % efficiency is significantly higher than the LWRs. That's mainly because the temperature of the steam is much higher. Okay, so let's go to each section to take a look. So let's start with the turbine hull, which we have both turbine hull and GIS hull. We start with turbine hull. And we're looking at the TG deck level. Again, I'm using the term deck. So you can see there's a high pressure, intermediate pressure, and low pressure turbine. So this one is high pressure, intermediate pressure, and low pressure turbine. And then you see the generators, exciters. So these are the main turbine turbo generator system, which sits on the TG deck. And then you see the century turbine on this side. You see the aerator on this side, which the low pressure feed water heater is underneath. And this one is a high pressure feed water heater. And you can also see the condenser underneath. You see the seawater pumps. And then there's cables to the transformers, which is outside of the turbine hull. Okay. This one we call auxiliary boiler. It's powered by oil, diesel oil. So what the purpose of this is, when you lose all the power, you lose all the fission power, you lose all the grid power, you can use diesel oil to power this boiler and supply steam to the century turbine. So you can still operate this for a while. And also it will help you to start the power plant. Okay, so let's take another look. Now we're looking starboard. So that means the other side of this picture is starboard, because we're looking starboard. As you can see, there's a total of 5 decks here: 1, 2, 3, 4, and 5. So 4 high pressure feed water heaters on 4 decks here: 1, 2, 3, 4. And then we have a 3 low pressure feed water heater on 3 decks here: 1, 2, 3. The aerator is on the main. The aerator is on the main deck on top. So this is the main deck. The main turbine is on the TG deck right here. So this deck is called TG deck, and the low deck holds the feed water pumps. So low deck, TG deck, and main deck. This is the other side. We call the looking port. Okay. So here's the century turbine right here. There's a desalination plant right here basically provide fresh water to the power plant. Then you have seawater pumps, 3 seawater pumps to pump seawater into the condenser to take away the heat from the steam. So it's basically the seawater is the ultimate heat sink. And then we have this small box here, actually 2 boxes. Those are the turbine hall fan room. So it circulates air in the turbine hall through these 2 boxes here. As you can see, the big condensers are here. You can see through it, you can see the high pressure feed water heater, low pressure feed water heater, the air reader on top, and then the chimney is for the auxiliary boiler. And you can also see the operation house, which people live there and operate the power plant. And you also see the steam pipes here, and also the power cables right here. Okay, here's another angle. We call it the looking after. So it's basically you're looking at the end or the stern part of the power plant. You can still see the feed water heaters, and you can still see the air reader, the turbine hall fan room on the main deck, the chimney on the main deck. The main turbines, if you can see it, it's on the TG deck right here. Here's the load deck right here. One thing I want to point out is there's some empty rooms here. It's a biaxial on both port and starboard side. And so this has 2 purposes. One is to allow the steam to, when something happens, when the steam will have a room to expand. So you can balance things into this biaxial. And also the structure, it also helps the overall structure of the hull. So here is a more closer look of the feed water pumps. So these 2 are the feed water pumps of the steam cycle. It's powered by the steam. Actually, here's a turbine, here's a pump. And then you have 3 hot well pumps. So all together, they're pumping the water into the steam generator. And you can see the desalination plant right here. And of course, on the TG deck, there's a generator exciter, and there's a cable, the 21 to 26 kV bus ducts, and also the generator circuit breaker. They're all on the TG deck. Okay, so those are the equipment in the turbine hall. So after the turbine hall, there's a GIS hall, which stands for gas insulated switchgear hall. So it basically holds the electric component. So you can see 3 main transformers, 1, 2, and 3, and also 1 spare transformer on the TG deck. And these transformers will raise the voltage from 21 to 26 kV to 420 kV. And then the cable goes to the high voltage circuit breaker, and it goes to the grid. It can go through the undersea cable, but there's also other options. You can see on the TG on the deck that's above the TG deck. Actually, there's a typo here. There shouldn't be a main deck. Should be TG deck. There's a two diesel generator. So each has a 1 megawatt output. So these two diesel generator are used for a startup of the power plant. So you can start this, first of all, you start this diesel generator, and once you get electricity, then you start using boiler, the auxiliary boiler. Remember, those two only get output of 2 megawatt, but the boiler with the central turbine can give you 15 megawatt. Then once you get to 15 megawatt, it will be enough to warm up the whole power plant and start the fission island, and then you can get the full power. So there's onboard storage of diesel and water, which is on the load deck, but it's not shown on this picture. It's underneath. So you can store a diesel for like a week or even 2 weeks for operation. Also, the water tanks, well, you get a desalination, so you can fill the water tanks as well. So here's another look. It's a plan view. So these are the generator circuit breaker, which is 21 to 26 kV. It's from the generator, and it goes to the transformer, the main transformers, and there's a spare transformer. And after transformer, the voltage is 420 kV. There's a high voltage circuit breaker, and this one is the house load transformer. It provides power to operate the power plant, but the main power is go out to the power plant from the stem. So, and again, you can see empty space. We call it ballaster on both sides. So again, all systems inside a double walled hull, and we call this hull. This will defend against the external impact, like airplane or ship. So those are the balance of the plant. So we got several references. We have a ThorCon fission island summary, which talks about this fission island. We have a ThorCon balance of a plant, which introduced in detail about what I just introduced. And we also have a conceptual modes of normal operation, which talks about the modes, the 1 to 14 modes in detail. So the terminologies used in this presentation are consistent with the terminology used by the IE. So that's all I have for today. Thank you all very much. I'm happy to answer any questions if you have any.
Okay, Mr. Kun, thank you very much. Sorry, Mr. Bob just leaving our meeting. So I try to moderate this meeting. There are 3 questions. One from Mr. Andang Widiharto. Question 1 is it true that during cooldown, all the fuel drain tank? And second, how to heat or to melt the molten salt during hot pre startup? And 3, is it true that in hot shutdown, the fuel remain in the core, how to maintain the molten salt temperature to remain in liquid state. And 4, why in the post-operation cool down must be transferred to other can. I think it is better the fuel remain in the same can while this can cool down. And number 5, how to transfer the fuel salt from the fuel drain tank back to the can. That the question from Mr. Adam.
Okay.
Please, Mr.
Yeah.
Kun.
Thank you for the question. Those are very good questions. So let me answer those questions one by one. The first question, during the cool down, the fuel salt is not filling the fuel drain tank. Instead, at the start of the cool down mode, the fuel salt will be transferred out of the fuel drain tank. So when we say cool down, it's the component that cools down. The fuel salt will be transferred to either another can or it will be transferred to the used fuel holding tank. So that's question number one. Question number two, so how to heat or melt the molten salt? Okay, so at the start, in the hot restart mode, the fuel salt is all the fuel salt are in the storage tank or vessel. So those vessels will have electric heating bands surrounding the vessel. Some of them will even have inserted heaters. So those electric heater will melt the salt in the vessel or in the tank. Then the salt can be pumped or pushed by helium to the pipes to other vessels. So it is important to have enough electric power to melt the salt at the startup. That's why there's a boiler to provide those power to melt the salt. Question number three. So in the hot shutdown mode, the fuel remains in the core or in the pot. Yes, that is true. How to maintain the molten salt temperature? So at the start of the hot shutdown mode, you will have enough decay power to keep the temperature, but as the time goes by, the decay power will decrease. So in that case, you will need extra power to maintain the temperature, and you could either use the electric power from the grid or the boiler powered by diesel can provide the heat. However, you can imagine it's not an ideal situation. So you don't want the can stay in the hot shutdown mode for too long. If you anticipate that you will be shut down for, let's say, a month, you don't want to keep it in the hot shutdown mode. You want to drain the fuel salt to the fuel drain tank. In that mode, you can stay for a much longer time. So question 4, why in the post-operation cool down must be transferred to the other can? Because the fuel salt has a lifetime of 8 years, while the can has a lifetime of 4 years. So after 4 years, even though the can has to be replaced, the fuel salt can still be used. So we want to use the fuel salt as much as possible to reduce the used fuel we're going to generate it. So that's why the fuel salt is transferred to another can for reuse. So that's only the main purpose is for reuse that salt. And if we not reuse it, it will be transferred to a used fuel holding tank. So basically the idea is to separate the fuel salt from the can. So can cools down by itself, while the fuel salt is in another fuel salt holding tank. So question number 5. So how to transfer the fuel salt from the drain tank back to the can? It has to go to the details of the fuel transferring system. So basically what's going to happen is the power is from the helium. So you use helium gas to push the salt around. So you push the salt out of the drain tank to another system, which not showing my slides, but there's details in the reports, which I will check with others within ThorCon to see if we can share those details. Those are some of the designs are new, not new, but very innovative ones. So I wanted to make sure that those information can be shared. But once we do the licensing engagement with Babaton, of course, all those information can be shared. Okay, so does that satisfy?
Okay. How about Mr. Anang? Are you satisfied?
Okay. Still in question number 4. ThorCon, I think has four plates to can, is right, and then 2 can is in operate and the other is not operate. I think if the can is in 4-year operation and then cannot be operated, this fuel can be stored in this can, and then the new can is installed to the other place. But if this fuel must be transferred to other can, it means that we will install empty can to receive the fuel from the previously operate. Is it like
Yes.
Yes? Oh yes.
Yes.
So let's install empty can, and the previous can after the fuel is transferred empty like this, and then this can is uninstalled and then we install the new can for operation like this.
Hello?
Hello?
Yeah,
Hello?
hello?
Yeah.
Okay. If we have 2 can place, what's the name? Call what's the name? To NP. For example, first we put in A side for the first operating can, and then after 4 years, the can is cooled down, not operate. So we can put empty can in B side to receive the fuel from the A side, like this. Okay, is it true?
Yeah.
Yes, and then
So, yeah.
True. Yeah, and then the A side will empty. So we uninstall the A side, and then we install new can with fuel in A side. It's true.
Sorry, Mr. Andang, I didn't hear every word you said. There's
As the
okay. The connection is not good.
the connection is not good. Yeah.
So maybe let me.
Okay. So
Yeah.
Or could you write in the chat?
Cap.
Okay, just write it.
Yeah, that's right.
And while we are waiting for Mr. Andang writing the question, so could you answer the question from Mr. Lim Peng Hong?
Yes,
Okay.
absolutely. Let me.
Okay.
So there's total of 5 questions here. So let me answer it one by one. The first question is for mode 2. When you heat up or sort, what is the electricity source or heating power come? So electricity source, there's 2 sources we can use. The first of all, if we have a grid power, then we just use the electricity from the grid. However, if we don't have it, then we use the auxiliary boiler to power the central turbine, which can generate 15 megawatt electric power that will be adequate to heat up the systems and sorts. So that's question number 1. Question number 2, for mode 8, what is the safety measure when the diesel fails and no grid power is available? So just give me a second. Let me just go to 8, mode 8. So mode 8 is the hot shutdown mode. In that case, so in the beginning of mode 8, you have efficient power. Of course, in the long term, you don't have the efficient power, so you have to rely on the diesel and the grid power. So when that fails, then you will open the fuel drain. You will open the freeze valve, let the fuel drain into the fuel drain tank. So that will let you enter mode 9. And mode 9 is a safe shutdown mode, so you can stay in mode 9 for a very long time. So that's for question 2. So basically, the simple answer is if you lose all the power, you enter mode 9. The question 3, for mode 9, when the fuel salt is drained into the fuel drain tank, and by some reason water enters and flooding the space surrounding FDT, is the subcriticality maintained? Yes, absolutely. So the FDT, the fuel drain tank, is designed such that regardless of the perturbation, the subcriticality will always be maintained. The K effective will always be smaller than 0.95. Question 4, can we omit the secondary loop? Is it necessary, costly? We have multiple loops because we want to separate the radioactive material from the BOP, from the steam cycle. So what happened is, first of all, the primary loop is the fuel, so it's highly radioactive. Because the secondary loop sort enters into the can, so it will be activated. So secondary salt loop will be radioactive. So then we have the tertiary loop, or we can call it solar salt loop. So that is not radioactive. So you can see the first and second loop, they're both radioactive. The third loop and the fourth loop, which is the steam loop, they're not radioactive. If we get rid of one of the loop, that means the steam will get in touch with a radioactive loop. If we have a leak in the steam generator, radioactive material will be released into the steam cycle, which is not what we wanted. That's That's the first reason. The second reason is that we believe by setting up these loops will prevent tritium from getting into the steam cycle. So our concept is to ensure that the steam cycle, the BOP, is non-radioactive. So perhaps by doing that, even though we're adding one loop, by ensuring the BOP is completely non-radioactive, we might be able to compensate the cost. So that's for question 4. Question number 5, is there any component equivalent to the LWR ECCS in your BOP sheet? So I suppose ECCS means emergency core cooling system. No, we do not need such a system, because in LWR, when you have a LOCA, the steam will get out of the system, which will in turn reduce the pressure. But when you reduce the pressure, it will exaggerate the generation of steam. So you have a positive feedback. That's why you can lose the coolant in a very fast speed. That's why you need to inject the coolant into the system to cool the fuel, which we don't have this phenomena because we're a low pressure system. We don't have to pressurize our system to maintain the coolant liquid. So there's no such phenomena that we have to take action immediately. The accident in our system develop very slowly, and it will self-contain. So, but we do have other safety systems like the drain system, like the freeze valve, which are adequate to ensure the safety. So we don't need a system that is similar to the ECCS in LWR. Okay, so that's question 5.
So the other question is from Mr. Helen Rafis. Mr. Lim, are you satisfied with the?
Yes. Okay. Thank you very much.
Okay. So from Helen Hafiz.
Yes.
Why is added the zirconium material to the fuel composition? This is different from the previous fuel composition.
So the reason of adding zirconium fluoride into the fuel source is to control the corrosion and to control the potential precipitation of the uranium and other elements. So the effect of adding zirconium, basically, if you have oxygen that left in the system, the oxygen will react and will increase the corrosion rate, may cause the precipitation of certain elements, including uranium. But by adding zirconium, if there's any oxygen left, oxygen will react with zirconium first. So it will mitigate the corrosion, it will mitigate the precipitation of uranium and other elements. Now, the zirconium fuel, the zirconium fluoride was used in MSRE, and it's used by the Chinese molten salt test reactor. I don't think there may be some documents from ThorCon that do not show zirconium, but I do think that probably for the reason that zirconium is only, we're only adding less than 1% of zirconium into the system. So they probably just for simplicity, they did not mention that. But I do think the conium has been used and is being used in the molten salt system by others and by ThorCon.
Okay, before we continue with Riono question, but I think Mr. Anang has already writing here. There are two can sites, A and B, for one power unit. If initially we put the can in the A site, after 4 years, we must put empty can in the site B just to receive the fuel from the A can. Is this true? Then the empty can in the A site will be uninstalled. We install the new fresh fuel can in A site. Is this true? Thus the A site will always fill with operating can, and the B site will always fill with the cooldown can. That's
okay.
the question.
Yeah. So
Do you
maybe let
understand?
me.
Yeah? Okay.
Yeah. Let me maybe start with going through the sequence. So let's say we have A site and B site. Let's say we start with A site and we put a new can into A site. Then we fill the can in the A site with fresh fuel, right? At this time, the B site is actually empty. So after 4 years, we put the new can, a new empty can, into the B site, and then we transfer the fuel from A site to B site. Okay, so then the can in the B site will operate for another 4 years, while the can in the A site will cool for 4 years, right? So then after 8 years, the can in the A site will be removed, right? And then we will put a new can into A site, right? But at this time, it has been 8 years, so the fuel salt cannot be reused. So fuel salt will not be pumped back to A site. The fuel salt will be pumped to a used fuel hold tank, right? The fuel salt will not be reused. And then we have to ship fresh fuel salt, fresh one, to the A site. So then we fill the A site with fresh fuel, and at the same time, the B site is empty, right? So after another 4 years, the B site is cooled for 4 years. So at the end of 12 years, the can in the B site will be removed, and the a new can will be put into B site, and fuel salt will be transferred from A site to B site. So that is the sequence.
Bagaimana Pak Andang? Okay. So I think there is question from Pak Wiryono. He is from Bapeten. How many external events you should consider to design the double hull as a containment?
So for this question, ThorCon's approach is to follow the guidance by the IEA. There's a external event that was listed in the IEA safety standards. We will go through that list to basically analyze every event that has been identified by the IEA. So that's the IEA part. But on top of that, we will also be studying the actual site that we're going to use. So I would expect that we need to work with Babakan and also based on the information we got from the site to add some extra external events. So having said that, it may also, by studying the actual site, it may also reduce or eliminate some of the external events listed by the IEA. So up to this point, because we haven't really started the site study, so all our design are based on the event that was listed in the IEA standard and codes.
Bagaimana Pak Wiryono?
Okay,
Okay.
thank you, Prof.
Okay.
Kun Chen.
Thank you for the question.
So there is another one from Sharif from Batan. The question related to the reactor protection system. How it look like? Can you elaborate on this? What reactor operating parameters can cause a reactor trip? What happens if the maximum power change is greater than 5% of full power per minute?
Okay, this is a very good question. So we're gonna have a workshop next week. We're gonna talk about the instrument and control system, which will include the protection system. We can elaborate that in next week's workshop. But just for the example you're mentioning here, what if the max power change is larger than 5%? So what you usually do, you have a neutron and a gamma detector. So you monitor the fission power by monitoring the neutron and gamma counts. So once you sense that the power is increasing at a higher speed than you expected, it will trigger the shutdown rods to be dropped into the pod, which will stop the chain reaction. But we should have a more systematic description about the protection system, which we will do in next week.
Okay. There is question from Azizul Hakim from Bapeten. If let's say earthquakes destroy the emergency power and freeze valve in such that the fuel remains in the can, is the CRs able to keep the core subcritical as the fuel temperature gets down?
So control CR, I
control rods.
assume control rods means CRs means control rods. Okay.
Yes.
Okay. So depends on how you destroy the freeze valve. So let's say if the freeze valve is broken, in that case the salt will leak out from the primary loop, and it will actually get into the can, and the can is actually connected with the fuel drain tank. So if there's any leak due to any reason that the salt gets out of the primary loop, it will flow into the fuel drain tank. But we haven't really started say in what situation you can actually prevent the fuel salt from drain to the fuel drain tank. So if that happens, let's say hypothetically the fuel salt remains in the can, the shutdown rod is in. When the temperature goes down, can we keep it to be subcritical? I'm not sure. We have done analysis, but I don't have the data with me today. I will go back to check with our neutronics people, and we can figure out at what temperature the fuel may go back to critical with the shutdown rod in. So I will follow up with this question with our neutronics people.
Mr. Kun, I think it is impossible because if after emergency powers gets off, so its freeze valve will be melt, I think.
I think what the question regarding is hypothetically that something happened, even though we haven't sort of that situation, but hypothetically you can, if something happened that you cannot drain the sword, so what's going to happen? I think that's that was the question.
Okay. And the other one from Azizul Hakim. Before I read the questions, please, those who want to ask can directly write in the chat, or you can directly ask to Mr. Kun. Okay. So the other question is from Azizul Hakim. As the core reactivity will change when the fuel speed changes, how do you compensate the reactivity change during load following or power increase by flow change?
Okay, so the question is about as the core reactivity will change when fuel speed change. Yes, so because of the delay neutrons, when we change the speed of the fuel salt pump, when we change the flow rate of the fuel salt, the reactivity will change. And we know it's an effect that is unique to the molten salt. So we want to avoid that. So during the load following, we keep the primary salt pump, the speed of the primary salt pump to be constant. So we don't change the pump speed. We don't change the fuel flow rate. We let the temperature change. So in that case, the reactivity is compensated by temperature change.
Okay, bagaimana Pak Ajis?
Okay. What mentioned in the previous slide about the flow change, is that the primary flow speed or secondary flow speed?
So we keep the primary loop pump speed constant. We change the speed of the secondary loop pump and the solar salt loop pump.
Okay, thank you.
Okay, it seems there are no other questions. I have a little bit question, Mr. Kun.
Yes.
I saw in the picture there is a thorium tank and also make-up fuel tank. What's the difference between both of them?
Oh, so the make-up fuel tank contains the enriched uranium. Okay. While the thorium fuel tank contains only thorium fluoride. So you can imagine thorium fluoride.
Okay.
It's natural thorium. So you can imagine when you add makeup fuel, you increase the load of fissile material, you increase reactivity. But when you add thorium, because thorium is it had to be, thorium is not a fissile material. So when you add thorium fuel, you decrease the quantity of fissile material in the core. So you reduce radioactivity. So we can adjust the reactivity by adding makeup fuel or by adding thorium fuel.
Okay. Is there any other question from floor? Okay, I think it's already 9:30, almost 9:40. So
there's a additional question.
Okay, from Nini Ramayani. Yeah. Why do you only use one module during load following? Why not both module A and module B in the test of the load following?
Yeah. Sorry for the confusion. We do use both. We do use both power modules, I'm only talking about one just for simplicity. So you can expect that both modules will do load following using the same method.
Okay. Do we have any question from others? It seems
there's a question about the Cold War.
Daddy Setiawan, yeah. Could you give me more explanation about the operation of Cold War for 4 years? Do you have any graph for explain the phenomenon?
Okay, so I don't have a picture with me, but the Cold War basically is a natural circulation of water. The water in the Cold War is heated by the heat from filtering tank and from can, and then the water goes into a heat exchanger, which is embedded in the cooling pond, which is a big water pond, and then it's cooled. It flows back to the Cold War. So, how do we operate for 4 years? First of all, this water. Natural circulation water is a closed loop, so the water is always there. But the heat exchanger at the cooling pond, it does evaporate water from the cooling pond. So if you don't do anything, let's say if you don't fill the water, if you don't do any maintenance, and then the water in the cooling pond will allows you to operate very close to half a year. Also, there's I don't know if you remember in the week 2 we introduced there's a basement water which can allows you to operate more than half a year. So if you don't do anything, it will cool passively. I don't remember the number, but I think it's about 200 days or more. But during operation, you can always fill the water. So I would say it can be easily operated for 4 years or even longer.
Gimana Pak Dadi? It's okay?
I have more explanation. Why do you use the water, not use air? Because air also you can use it, and then is for the normal circulation from the natural, and so maybe you don't need to make some tank for the water, like.
We're using water. I think it's based on the calculation we have done. I cannot comment on the exact reason because I don't have the data with me, but in generally speaking, if you look at a power plant that has low power density, like the gas-cooled power reactor, like small test reactor, they can use air, the natural circulation of air. But if you want to increase the power density, you increase the power of the reactor, you will find that it's challenging to just use air. Water needs to be introduced. And even for a high temperature gas cooled reactor, there are certain parts they use a water circulation instead of air circulation. But I think in general, it's air, the cooling capability of air is lower than water, so it's more suitable for a smaller, lower power density reactor. In our case, ThorCon is a high power density, high power power plant, so water may be the better choice for ThorCon. And also having in mind that the ThorCon power plant is a ship, it's sitting in the water, so it got a plenty of water to be used.
Okay, thank you, Professor Kun Chen. Thank you, Pak Hedi.
Okay, the last question,
Thank
I
you.
think, because we already have 9:45. How the dose rate above red tank during normal operation? From Mr. Hendra from Bapeten. Yeah.
Yeah, it's a very valid question. Unfortunately, I don't have the number with me in this workshop. I will go back to find this number, and maybe I will get information to Ms. Hedy, and he can pass this to you.
Okay, thank you. It seems that no question more, and the time is also almost 10 p.m. So I should try to close this fourth meeting session by concluding some notes as follow. There are three parts of presentation. One is normal operation, two is load following power operation, three is balance of plant. And second, the operation mode of TMSR 500 for the normal operation has been presented in this week training session. Since the TMSR 500 is modular reactor, so the operation mode is based on the CAN mode rather than PAN mode. CAN consists of the reactor core and primary system, heat exchanger and pump, including uranium and thorium makeup tank. There are 14 operation modes for the normal conditions, from M1 to M14, I think. Yeah. And the operation parameters such as key effective, percent power, and fuel temperature and fuel location are also described in the session. The TMSR 500 can be operated by the load following power operation. Maximum power change rate is 5% of fuel power per minute, compared with the typical other nuclear power plant with the typical power change rate is 1%. So I think that is the conclusion. Because it's already 9:45. Today discussions I'm going to close, and thank you for presentation, Mr. Kun, and to everybody in this meeting. Because before I close this meeting, it's better to turn on the video for the photo section. Could you help us, Navan?
Yes, Pak Hedi.
Okay.
In fact, Ms. Hedy, I suggest maybe next time we take the picture when we start.
Okay.
I know there are people leaving after more than 2 hours.
Okay, thank you. Okay.
Or in the middle of the lecture.
Yeah, in the middle,
yes,
I think better.
Yes.
Okay.
Okay, everyone. I will count for the first slide. 1, 2, 3. And then for the second slide, 1, 2, 3. Okay, thank you.
Okay, thank you, everybody. See you next week.
Thank you, Prof. Kun.
Bye-bye, Mr.
See you
Kun.
next
Thank
week.
you.
Bye.
Bye.
Thank you. Thank you.
Thank you, Professor Kun
Thank
Chen.
you. Makasih semuanya ya. Mohon
Terima kasih,
maaf
Pak Hedi.
Malam Edi, terima kasih.
kalau saya bahasa Inggrisnya belepotan.
Enggak, mantap kok bahasa Inggrisnya, Pak Hedi.
Oke, see you.
Selamat malam, Bapak.
Malam semuanya.